All right, good morning, ladies and gentlemen. I'm very glad you made it back home, back to CTTC after the social last night. We have a networking and experimentation day today, and we start off the day with a presentation on mobility management and integrated Macrocell-Femtocell LTE networks, and that is research conducted within the GreenNet project, and Christos, who has been with us now at CTTC for a long time, working on various issues related to green communications, energy efficiency, femtocell cellular networks, will give a very brief overview of the GreenNet project, and he will hand over later on to Dionysis to continue with the actual technical presentation. Now, before we go on, we have a little bit of a fractal schedule, so we're going to have this 1 hour, then we have another presentation half an hour, then we have a coffee break, which maybe we do a little bit shorter, so we then have another break, short break in between the other presentations, so it doesn't become too long. So I wanna break today and stop and finish the Femto school just before lunch, which will be around 2 o'clock today. All right, so okay, the floor is all yours, Christos.
Thank you, Misa. The talk of today is about energy efficient mobility management for integrated Macrocell-Femtocell LTE networks. It's a joint work with my colleagues Dionysis Xenakis and Nikos Passas from University of Athens and Lorenzo Di Gregorio from Atlantic. This is the table of content of the presentation today. This presentation is in the framework of different research-funded projects. As Misa said, GreenNet, a Celtic project Green T, C2Power, that is a FP7 project about green mobile terminals, and a national project funded by the Ministry of Education, CO2 Green. A very brief overview about GreenNet. GreenNet is is a Marie Curie initial training network. It's a joint training and research network that focuses on the analysis, design, and implementation of energy efficient wireless networks. What is an initial training network? An initial training network are aimed at improving the career perspectives of early stage researchers at the first 4 years of their career. How? By implementing an international network of participants, by recruiting and hosting eligible researchers, and offering a complete joint research and training program. The involvement of the industry in such a kind of project is very high appreciated by the European Commission. This is a picture of an ITN network where each partner hire different ESRs, early stage researchers, and there is a change of personnel between the different partners. This is a consortium. We have a very well-balanced consortium. 3 research centers, 3 universities, 3 SMEs, and a big company, Cassidian. All in all, we have 612 person months, and we have hired 17 early stage researchers for 3 years each one. The main objectives is to recruit talented ESR, early stage researchers, to develop a personalized training and career plan for each one, to understand that this research program will help them to understand and address the key research challenges on energy efficient communication. We will offer them top-level training and research program, and will complement these activities with complementary research, seminars. Finally, the project will be the guide that will help the ESRs to build a bridge from the current position in the academy with their future position either in the academia or in the industry. As you can see, our training program includes high-level research program, interaction with well-structured research team, participation in the research-funded projects, participation in international conferences and workshops. We organize a series of seminars in different research topics, from modeling, simulations, stochastic model, closed layer, cognitive, MIMO, multi-objective optimization, self-adaptation. We also have seminars for complementary activities, like writing scientific papers, understanding patents, presentation skills, project management and EU projects, market exploitation. We also organize 2 workshops, 2 industrial dissemination days and the final conference, and we have training through the so-called secondment, where ESRs from one partner move to another one in order to have exchange of knowledge. The research challenges, we introduce the concept of spatial modulation at the physical layer. We will develop energy efficient MAC and radio resource management techniques. We also introduce network coding for energy saving at layer 3. And we are trying to exploit short-range cooperative communications and cognition in order to save energy in a wireless terminal. Finally, I would like to announce CAMAD. The 17th CAMAD will be organized in Barcelona from 17 to 19 of January. We can submit a paper, and if someone wants to help us as a TPC member, just drop me an email. Just to say that the CAMAD is organized under the umbrella of Green Project. Now Dionysis will continue with the technical presentation about energy efficient mobility management between macro and femtocells. That's all for me. Thank you very much.
Good morning. I hope you're ready to spend some energy in order to hear some things about energy efficiency. As you may all know, femtocells are short-range, low-cost cellular access points installed by the consumer, which utilize the consumer's broadband backhaul to reach the mobile operator's network, given through a DSL line. And they typically operate in the mobile operator's licensed spectrum, and they also support up to a few users, for example, up to 4 users. They also radiate significantly lower power compared to the macrocell infrastructure, example given up to 20 dBm. However, femtocells are also subject to access control, where we identify 3 access control types: the closed, the hybrid, and the open access. I'm sure you have already discussed about the access modes. Now here's a typical example of how the user equipment receives service from an installed femtocell, which reaches the mobile operator's network through the broadband access backhaul of the user. Now, from the mobile operator's perspective, we can say that femtocell deployment reduces the capital and operational costs expenditure for the mobile operator, given that they utilize the consumer broadband backhaul and they are installed and managed by the end user. They also improve intercoverage. They enhance the overall system capacity, resulting in higher spatial frequency use. They greatly lower power transmissions, and they decongest nearby macrocells. However, they also necessitate the employment of self-X capabilities, advanced interference management, mobility management, security management, and network management as well. From the end user's perspective, the femtocell user perceives improved intercoverage, enhanced system capacity, and then throughput. The femtocells also prolong the battery handset lifetime of the user, and they can also lead to preferential charging for the femtocell user. However, all these gains are derived at the cost of potentially more frequent handover execution events and thus service interruption in medium to high mobility scenarios. I'm sure you have already discussed about self-X capabilities and interference management. I would only like to point out that apart from the cross-tire interference between the different tires, the macrocell and the femtocell tire, another challenge is the inter-tire interference within the femtocell tire itself. Now, let us now focus on the mobility management for the integrated macrocell-femtocell network in general. Mobility management is quite challenging given the fact that we have an unplanned femtocell deployment pattern. We have the access control restrictions, we have network densification, and we have short-range communications which are subject to high femtocell sensitiveness to user mobility. And the unplanned deployment also results in divergent interference level at the cell sites. And we may also have a divergent behavior between the femtocell nodes themselves, given that we have the employment of self-optimization techniques. Now, mobility management can be broken down in 5 important key challenges. We have the femtocell characterization identification, we have access control, and we also have the normal 3 aspects of mobility management, which are network discovery, handover decision, and handover execution. Now, here's a typical example of the dense femtocell deployment within a macro. Here's the macro, here's the user equipment, where the user equipment receives a lot of signals from nearby cells, and all this network densification leads to the challenges we will discuss in the following slides. At first, let us now focus on the femtocell characterization identification procedure, which consists of how to distinguish femtocells from macrocells. This problem originates from the fact that we have a limited number of physical cell identifiers, and this is also known as the PCI confusion problem. Some solutions to the limited number of physical cell identifiers necessitates the reuse of the physical cell identifiers within the dense network layout. So some solutions to this problem are the hierarchical cell structure, to use a separate PLMN ID between the femto and the macrocell tires, to reserve some carrier frequencies or physical cell identifiers for femtocells and only, or to make the user equipment to acquire the cell global identifier of its cell, which is unique in a worldwide scale, network-wide scale. Now, the problem of access control can be broken down in 3 tasks. At first, we want the user equipment to be able to identify which femtocells, closed or hybrid access femtocell, it can access. It's an information that should be maintained at the user equipment side. On the other hand, we need the femtocell nodes to enable the user equipments to identify that what kind of access type they support. Moreover, we have the issue where we need to know who will be responsible for ultimately performing access control. Here's an example of the PCI confusion problem I mentioned before, where we can see that we have 8 physical cell identifiers which are being reused within the network. So here we have the PCI 4 for this femtocell. We have also a PCI for the macrocell as well. And so the user equipment who performs network discovery senses more than 1 physical cell identifiers of the same ID. So upon his reporting to the macrocell, to his serving cell, here's the macrocell, the serving cell is unable to make a one-to-one mapping from the physical cell identifiers to the target cell that he may want to hand over to. So this is the PCI confusion problem. and originates from the limited number of physical cell identifiers. Now, moving on to the network discovery procedure, as you may all know, network discovery is usually performed by sensing the pilot or reference signals broadcasted by the cells. Given that femtocell deployment is unplanned and that we have a potentially dense femtocell deployment layout, and given that we have a limited number of physical cell identifiers which are being reused, each cell is unable to transmit and broadcast a complete neighbor cell list, meaning that the neighbor cells which in its proximity, in order to facilitate the user equipment during network discovery. To this end, we need to migrate from network control network discovery, which is network configured network discovery, to user equipment autonomous network discovery, where the user equipment can use autonomous function in order to perform cognitive and cooperative network strategies in order to acquire the nearby cells. And we also need to be smart enough in order to avoid unnecessary search, given that we are unable to access all the femtocells within range due to access control. During network discovery, we have to take into account that autonomous search has some performance trade-offs. On the one hand, we have an up-to-date neighbor cell list, meaning that we will find all the neighbor cells within our proximity, versus the service interruption overhead that is introduced during our discovery, the energy consumption overhead, as we also spend some energy in order to sense all the cells nearby, and the potential and throughput degradation due to the DRX cycles which are required for network discovery. Now, the problem of Handover decision can be stated as follows. Given a neighbor cell list for a tagged user, the serving cell has to decide whether handover to a neighbor cell is required or not. And during the employment of the handover decision algorithm, we can employ various optimization criteria, which we'll discuss in the following. The challenges of handover decision making are that we need to, in the context of femtocells, of course, is the fact that we need to resourcefully utilize the femtocell superior characteristics in terms of enhanced system capacity, quality of service, lower transmit power, and so on. We also need to mitigate the negative impact of user mobility, which originates from the short range nature of communications. We also need to consider the consequential cross-tier and intra-tier interference of the outcome of our decisions, while we also need to be energy efficient, meaning that we need to make use of the opportunity given to us by the femtocell infrastructure in terms of enhanced energy consumption. And by doing so, we can minimize the energy expenditure for both the access network, the base stations, let's say, and the user equipments as well. Now, the handover execution. The handover execution increases the signaling overhead which passes through the network, and it also results in non-negligible delay during the transition from a cell to another cell, which can lead to service interruption and/or service outage. Now, the handover execution in the context of femtocells should be reassessed, and the network architecture of the network as well, given that we have a high femtocell deployment pattern, which increases the number of handover execution events, and it also increases the consequential signaling overhead. And by taking into account that the handover decision, the handover execution is strongly correlated to the handover decision making, we also have another goal, which is to perform more sophisticated handover decisions. And this is the open issue of energy efficiency, which I have previously mentioned, where we have the short transmitter-receiver range that can greatly reduce the energy expenditure. Now, according to the report in LEAM, a femtocell deployment tire, the deployment of a femtocell tire can reduce the transmit power for the access and the user equipment by 4 to 8 orders of magnitude. However, according to the report in COW, we also need to take into account, in order to calculate the energy consumption gain, that femtocell deployment also increases the radio frequency interference due to the fact that we have unplanned deployment. This unplanned deployment also reduces the system capacity per tire and also condenses the energy consumption gain. Now, femtocell self-optimization is another design option which can also lead to reduced energy consumption for the network. Let's say the report in ASRAF, where they use some pilot adaptation mechanism. Okay. Now, let us now focus on the mobility management for the LTE network and discuss about LTE Advanced as well. And the release 9 of the third generation partnership project for the long-term evolution system is one of the first standards to provision the deployment of femtocells. The standard includes and describes the cell identification, access control, and mobility management procedure for closed and hybrid access femtocells. In the context of LTE, user equipment is a member of a closed subscribers group, either if it can utilize a particular set of closed access femtocells, or if it receives prioritized service of, on a particular set of hybrid access femtocells. Now, LTE Advanced, also the release 9 of LTE is also known as LTE Advanced, enhances the support of home minute Bs, as we will discuss in the following. Now, here's the architecture of LTE release 9, where we can see an X2 interface between the inode Bs, which, however, is absent between the home inode Bs, which are the femtocells. And we also see that the inode Bs, home inode Bs, are interconnected to the evolved packet core through the S1 interface. And we can also say that the deployment of the home inode B gateway is optional, and if deployed, the home inode B gateway acts as a concentrator for the control plane between the evolved packet core, which is the mobility management entity, secure gateway, and the home inode Bs. Now, the gateway appears to the MME as an inode B, while it appears to the home inode Bs as an MME. It's a type of abstraction for the network. Now, different from LTE release 9, LTE, LTE Advanced, which is the release 10 of LTE, provisions the interconnection of home inode Bs with an X2 interface, which can enhance the mobility and interference management in LTE Advanced. However, note that an interconnection, a direct connection from the inode Bs to the home inode Bs is not available even at LTE Advanced due to the cost for infrastructure and the consequential signaling overhead. This is some. If we want to compare LTE release 9 to LTE release 10, we can say that release 10 supports the X2 interface between home inode Bs. However, the handover between two femtocells takes place between the X2 interface only if no access control is required at the mobility management entity, and or if the target femtocell home inode B is of open access, so access control is not required. The PS5 interface is also provisioned in the standard to support the local IP address mechanism. And as we have previously mentioned, both releases do not support X2 interconnection between a home inode B and an inode B. Now, let us now focus on the particular characteristics and the resolution of the 5 problems that we have previously discussed for the Femtocell deployment in general. This is how the LTE Release 9 resolves these issues. Okay, we have 504 physical cell identifiers in LTE, which we need to reuse due to the network densification when we have Femtocell deployment. In order to resolve the PCI confusion problem, the LTE cells broadcast in the system information block type 1 every 8 milliseconds approximately an unique identifier, the EU Transcell Global Identifier. So the user equipment acquires this global identifier in order to uniquely identify which cell the serving cell should hand over to, if required. Now, for the access control, the user equipment identifies the accessible closed subscriber group femtocells by maintaining locally a whitelist at his terminal. On the other hand, we have the broadcasting of a closed subscriber ID and an indication bit from the Femtocell nodes that indicate what is the ID of the access supported and what is the type of the access supported. The indication bit is set to true if we have closed access femtocells, or to false if we have hybrid access femtocells. Now, the access control is always performed in the mobility management entity we have previously shown in the network architecture. To this end, we always have to pass the handover execution signaling through, in LTE Release 9, through the core network. If we have an inbound handover to Femtocell or to outbound from Femtocell, inbound handover only to Femtocells, we need to pass all the execution signaling through the MME and the S1 interface in order to perform access control. As we have previously mentioned in LTE Advanced, this is not required always. Okay, now network discovery in LTE. Network discovery is based on the reference signals which are broadcasted by each cell, and is based on sensing the received power on reference signals. We distinguish two different cases depending on the user equipment state. When the user equipment is in the idle state, the RRC idle state in LTE, the cell selection and reselection procedures to close subscriber group cells is based on user equipment autonomous search and in network prioritization, which is broadcasted by the cells. Now, cell selection, reselection is something like a handover in the idle mode. Okay. This is very important, given that the LTE for the first time allows an autonomous search from the user equipment side, which does not necessitate network configuration always. And this search function is not standardized and is an open issue how to do autonomous search, and determines itself when and where to search in order to discover some femtocells, nearby femtocells. Some additional information can be provided to the user equipment in order to facilitate the network discovery. Now, when the user equipment is in the connected mode, the RRC connected state, we have a normal measurement and mobility procedure in terms of network discovery, where we have user equipment assisted network configured network control network discovery. However, LTE also provisions for the employment of a proximity indication procedure, according to which the serving home node B can configure the user equipment to autonomously infer whether it is nearby a femtocell or not. So it does not provide the specifics of the target cell or the frequency to sense, but the user allows the user equipment to determine whether it is nearby a femtocell. The proximity indication in terms of network signaling is performed as follows. We have the source node B who reconfigures the user equipment to initiate the proximity estimation procedure. Upon determining that the user equipment is nearby a femtocell, it reports back the proximity indication, and the source node B reconfigures the user equipment to make some measurements for the femtocell under scope. Accordingly, the user equipment derives some measurements and reports them back to the source node B, where the source node B reconfigures the user equipment in order to resolve the PCI confusion problem by acquiring the system information of the target cell. Remember that we have the problem of PCI confusion and we need to acquire the ECGI of each cell in order to uniquely identify which femtocell we refer to. Accordingly, the user equipment in step 6 derives the system information and reports it back to the source node B. So by these steps we have network discovery, and we also have the femtocell identification procedure in LTE. Now in the handover execution, the outbound handover from a femtocell in LTE follows the normal LTE handover procedure as the one followed for macrocells. However, the inbound handover to a home node B to a femtocell is different from the normal procedure in 3 aspects. At first, we have the proximity estimation procedure we have previously described. Secondly, we have the PCI confusion problem which we need to resolve, and it is resolved by the signaling we have previously discussed as well. And finally, we also have the employment of access control in order to verify the membership status of the user equipment on the target cell. Access control in LTE is always performed at the MME. This is the handover execution, inbound handover execution signaling in LTE, where the first 7 steps are the same with the steps we have previously discussed for network discovery and femtocell characterization. In step 8, you can see that we have the employment of handover decision, and in step 10, if we assume that we have decided on a handover to the target home node B, in step 10, we perform access control at the MME. Accordingly, if access control is valid, then in step 13, the target home node B, which is about to receive the user equipment for service, also validates the membership status of the user equipment and forwards the handover command to the serving cell and the user equipment as well in order to proceed. Now, at the remainder of this session, we will focus on the handover decision making. Current literature on handover decision making, meaning current handover decision algorithms, typically prioritize femtocell access over macrocell access according to speed and receive signal strength based handover decision rules, based on the traffic type of the ongoing user connection and the minimum required receive signal strength, or the estimated distance between the user equipment and the target cell. A more detailed state-of-the-art, I have some backup slides which I think it would be difficult to discuss in this session. Okay. Also, current algorithms also focus on have as an optimization criteria to minimize the number of handover execution events in the system. meaning that they tend to extend the utilization of a particular femto or macrocell, typically femto. And finally, the current literature also typically employs the strongest cell handover decision policy for handovers between macros and femtos to femtos, intra-tier handovers, where the strongest cell policy can be summarized as follows. We have the serving cell that executes a handover when the received power on the reference signal received power of a neighbor cell exceeds over the RSRP status of the serving cell plus a handover hysteresis margin for over a time to trigger time period. Okay, this is the handover strongest cell handover decision policy. Now, the weak aspects of current literature can be summarized as follows. When we try to minimize the number of handover execution events, we can rise the radio frequency interference and degrade the SNR performance as we're striving to sustain a connection with a femtocell, even though we have moved to another area, because we need to minimize the handover probability. Also, we can reduce the femtocell utilization potential, given that we employ the strongest cell policy. Moreover, current literature typically does not take into account the impact of having different transmit power on the reference signals, or the fact that we have different interference levels among the cell sites due to the unplanned deployment. The interference level is not the same as we can approximate in the macrocell layer when we have femtocells. Moreover, the performance of the proposed algorithms in terms of interference and energy consumption is typically not investigated. Finally, the employment of the strongest cell policy for intra-tier handovers, even though it can improve the propagation characteristics between the user equipment and the cell, it is interference agnostic, meaning that it does not take into account the interference level at the cell sites. So we have the SINR, which is the received power divided by the interference and the noise ratio at the cell site, and the strongest cell does not take into account the denominator. It only takes into account the received power, but the SINR is closely related to both. Okay. Now, beyond state of the art, we need to employ interference-aware handover decision-making. We need to guarantee a mean SINR target for the ongoing user connections. We need to achieve a good performance trade-off between sustaining a low handover probability and extending the femtocell utilization time. We also need to be backwards compatible with LTE. And finally, we need to be energy efficient, meaning that we need to exploit the energy saving potential offered by the femtocell infrastructure. Now, our approach can be summarized as follows. At first, we have a method which enables us to estimate the expected user equipment transmit power on a per candidate cell basis. And in order to do so, we incorporate standard user equipment and EU transitional quality measurements, and we also introduce, during our estimation, the SINR target for the current link of the user. Accordingly, based on this estimation procedure, which enables us to accurately estimate the transmit power of the user equipment per candidate cell, we propose a novel energy-efficient handover decision policy, which initiates a handover, decides on a handover to a candidate cell, to the candidate cell with a minimum required transmit power. Please note that transmit power is the key energy consumption contributor, and so minimizing transmit power can also we can say that also minimizes the energy consumption overhead as well. Finally, we are backwards compatible with LTE, given that we incorporate standard LTE signal quality measurements, and no further novel methods are required. And we also employ the proposed policy by introducing an adaptive handover hysteresis margin. But now, based on this policy, we propose a novel handover decision algorithm which takes into account some more information, and we describe the required handover context acquisition signaling for acquire the measurements from the target cells and the user equipment as well. Based on the evaluation methodology of the Femto forum, we perform some simulations and derive some simulation results in which we take into account the impact of the algorithm in terms of consequential radio frequency interference and energy consumption. Now, don't be afraid, there are only 3 slides with some simple notation and maths. In brief, we have the n corresponding, all the notation corresponds for a tag time interval t. N corresponds to the LTE band set, which we can utilize over the LTE network. Gamma subscript target, gamma bar subscript target for user U, which is a superscript, is the mean SNR target for user U. The set of LTE cells operating within band L is denoted by Cn, and the set of LTE user equipments receiving service from Cn are denoted by Un. The candidate cell set for a tagged user U is denoted by L subscript U, and for 2 tagged network nodes, which can be either Femto user, an LTE user or an LTE cell, X and Y, we denote the mean transmit power by P bar subscript X for a tag time interval T, which is the superscript, and the mean node power by the symbol here, and the mean channel gate between node X and node Y, H bar X to Y superscript T. These values are averaged over a tag time interval T. Okay. Now, I think we all know that the mean SINR target for the uplink direction, meaning from user U to the serving cell C, for a tag time interval T, is given by the product of the user equipment transmit power times the channel gain between the user and the serving cell, divided by the interference caused by in-band operating cells, which is this factor, plus the interference caused by in-band operating users, plus the thermal noise at the serving cell. Okay, this is the SNR expression for the uplink direction. Keep in mind the previous equation. Now, LTE, as we have previously mentioned, in 36.214, provisions for a wide set of network signal quality measurements, in general, performed either by the user equipment or the LTE cells, the UTRAN part. Now, we have the reference signal received power, which is the received power on the reference signals. We have the EUTRAN carrier RSSI, which is the received interference at the user equipment side. We have the RSRQ measurement, which is something like the SINR estimated on the user equipment side. And we also have from the cell sides, we have the downlink reference signal transmitted power, which is the transmit power on the reference signals, not for users, for the reference signals and only, and the received interference power, which is the interference at the cell site, averaged over all the operating bandwidth of the cell for a tag time interval T. Now, bear in mind the definition of the RSRP measurement for a tag time interval t from cell C to user U, we can say that the RSRP measurement corresponds to the product of the transmit power on the reference signals times the channel gain between the target cell and user U. Assuming a symmetric channel gain from user U to cell C and the way back, we can estimate the channel gain between user U to cell C in the uplink direction by the RSRP measurement divided by the transmit power on the reference signals. Now, based on the previous equation and these equations here, and by using the mean SINR target of user U, substituting it here, we can derive to this equation here at the right hand, where it is an estimate of the expected user equipment transmit power from user U to cell C, which is based only in standard LTE measurements. So we have an accurate estimation based on measurements of the target cells and the user equipment itself for the user equipment transmit power on a per cell basis. Note that we distinguish the case where we have the target cell and the serving cell operating within the same band in order to subtract the interference caused by the ongoing user connection to the candidate cell. Now, based on this system model, we can summarize the strongest cell handover decision policy as follows. The strongest cell handover decision policy handovers to the argument of the maximum RSRP measurement for every candidate cell C in LU, the candidate cell list, where the RSRP measurement of the target cell should exceed over the RSRP measurement of the serving cell plus the policy-defined handover hysteresis margin for over a time to trigger time period. Note that the HHM, the adaptive hysteresis margin value, is used for mitigating user mobility. It's a margin in our decision, and all the values are taken in decibels. Now, by taking into account that the RSRP measurements only includes the product of the transmit power and the reference signals times the channel gain between the user U and cell C, we can say that the strongest cell handover decision policy does not take into account the actual radio frequency interference levels, so it is interference agnostic, or the actual power transmission on the reference signals. It only takes into account the product of the transmit power. To this end, we can say that the employment of the strongest cell handover decision policy does not necessarily improve the SINR, which we have previously shown that also depends on the interference on the denominator, and it does not necessarily reduce the user equipment transmit power due to the interference again. And so it can result to increase the user equipment transmit power on the average and radio frequency interference at the cell sites as well. Now, taking this into account, this is the last slide with some expression, so okay. Based on these observations, we propose a new user equipment power consumption minimization handover decision policy, where our goal is to hand over to the candidate cell with a minimum required user equipment transmit power. Now, having as a starting point the condition of moving towards a target cell C with lower power transmit power compared to the current radiated on the current serving cell over a time interval, time to trigger, we can come up with the following handover decision criteria, which is exactly the same with the strongest cell handover decision policy criterion. However, we have this adaptive handover hysteresis margin, which in fact transforms the strongest cell criteria to the required condition of moving towards the cell with a minimum user equipment transmit power requirements. And this adaptive handover hysteresis margin is is based on standard LTE measurements, which is derived based on the previous equations. Okay. Now note that we have the adaptive Handover hysteresis margin subscript C as well, in order to have a margin during our handover decision phase. Now, based on this policy, we propose a novel handover decision algorithm, which also takes into account some additional handover context parameters regarding the residual cell capacity in users on the target cell and the potential power limitation in the candidate cells and the user equipment membership status on the target cell as well. And this algorithm uses a maximum handover decision time horizon in order to control the decision-making delay, and also deals with random handover context acquisition delay by using a queue structure in order to skip cells which we have no information about them yet. Now, we will not discuss the proposed algorithm in depth, so we will focus on how we can derive all the parameters, the standard LTE measurements, the residual cell capacity on the target cells, and so on. How are we going to commute this context to the serving cell, which makes the decision? In order to do so, we identified two different network signaling approaches, the reactive and the proactive one. The reactive one is we have the serving cell, which makes a request to every candidate cell that for the tagged user equipment, and waits for the response, the reply of these cells in order to derive the context. On the other hand, we have the proactive approach, where we assume that there exists a core network entity that maintains and gathers all the required context from each cell on a periodic basis. So the serving cell is not required to make the request to the target cells, but acquires the required context from the context-aware core network entity. Here is the reactive network signaling approach, where based on the standard handover inbound handover execution procedure, we can see the forwarding of the request towards the target cell in order to acquire the context of the serving cell. And here is the proactive approach, where we have the context-aware mobility management entity, which derives this context on a periodic basis from the target cells. And so, upon handover decision triggering here, the serving cell acquires this context on demand to the MME and not to the target cells. The reactive approach does not require any modifications for the network. However, the reactive approach requires some small capabilities at the MME side in order to gather and maintain the required handover context. Moreover, the overall network signaling of the reactive approach is highly correlated to the occurrence rate of handover execution events. And while a more frequent yet more deterministic signaling overhead is expected for the proactive approach, given that the context is derived from a context-aware core network entity. Now, here we have the numerical results for our algorithm, where the simulations were conducted according to the evaluation methodology of the FEMTO forum, and we have a main LTE cluster area which consists of 7 LTE cells. This is the main area. Each cell has 3 sectors, and we copy the cluster on each 6 sides based on the wraparound technique. We have the concept of femto blocks, which are a set of blocks of apartments with a road dividing them and so on, where we use the dense urban environment model from the FEMTO forum evaluation methodology document. And we have 2 basic simulation parameters. The first one is the femtoblock deployment density, which corresponds to the percentage of the main LTE cluster area covered with femtoblocks. So we have the area, the main area, and the femtoblock deployment density corresponds to the percentage of the area covered with femtoblocks. And we also have the femtocell deployment ratio, which is the percentage of femtocells installed, the percentage of apartments with a femtocell installed within a femtoblock, meaning that how many of the apartments are equipped with a femtocell within a femtoblock on a percentage rate. And we have compared the proposed algorithm against the Strongest-Cell-based algorithm and the proposal in Zhang of ICCSM 2010. Here is the mobility and path loss models used. And here is a snapshot of the main LTE cluster area of our simulator, where we can see the cluster, the main cluster area. We can see the femtoblocks. We use a dense urban environment femtoblock, where there is some femtocells per apartment and so on. Here is our first result. We have the average user equipment power consumption, and we have the percentage of femtoblocks within the main LTE area, the percentage of area covered with femtoblocks. We can see the blue line corresponds to the Strongest-Cell algorithm, the green to the Zhang algorithm, and the red line to our algorithm. And we also have two graphs per algorithm, given that we have used a different femtocell deployment ratio within the femtoblock. Now, we have observed that depending on the femtoblock deployment density within the main LTE cluster area, we can sustain an up to 90 dB gain, user equipment transmit power gain, compared to the Strongest-Cell handover decision policy, and up to 90 dB gain compared to the algorithm in Zhang. And in terms of energy consumption per bit, joules per bit, we have observed an 85% gain, up to 85% gain compared to the Strongest-Cell algorithm, and up to 66% gain, energy consumption gain in joules per bit compared to the proposal in Zhang. Interestingly, we have also observed some noticeable gain for the LTE cell power consumption owing to transmit power only, which can be up to 30 dB compared to the Strongest-Cell algorithm, and up to 7.5 dB compared to the algorithm in Zhang. Here is a result that connects the energy consumption with the interference, where we can see that when we try to minimize the transmit power and the energy consumption, we also result in reduced interference for the network. And this is the graph for the user equipment side, where we can observe some gains, and for the cell side, where we also have some gains compared to existing algorithms. In this graph, we can see the handover probability, which rises as the femtoblock deployment density increases. And we can see that the handover probability of both the Zhang and our algorithms are higher compared to the Strongest-Cell algorithm, given that they are femtocell aware, while the Strongest-Cell is not femtocell aware and only picks the cell with the strongest power on the reference signals. However, it is shown that our algorithm sustains a lower handover probability compared to the Zhang algorithm, which we can also reduce by using a higher handover margin, which is the second parameter on the criterion. And by using a higher handover margin, we also condense the energy consumption gain, which is also, however, high enough compared to the other algorithms. Now, our future work includes adaptations of the algorithm for LTE Advanced, enhancements towards sustaining a lower handover probability while sustaining a comparable energy consumption gain as well, and study with respect to the required network signaling overhead for acquire the context, and of course simulation results. Here are some references. Thank you very much for your kind attention. So,
thank you. That's very nice, actually. You've given a really complete picture. I didn't expect that. So nice simulation results as well. Are there any questions from the audience? If not, I have a question on the energy, energy gains. You know, people get always very excited about the numbers, 80%, 20%, whatever. But it's always the question with respect to what did you really measure? Because you need to bear in mind that the terminal is switched on when it does. You know, it's when you do handover, it means you're actually using data and stuff like this. When you do the calculus, you figure out that the screen consumes actually maybe 50% of the energy. Microcontroller and all the processing maybe another 30%, and you go down, and in the end you figure out that the physical layer, your radio stack only consumes maybe 5%. So the big question is, you know, what's the global impact on your terminal? Okay,
yes, that's right. These results correspond to the energy consumption per bit by taking into account only the transmit power, not the all peripheral operation of the terminal.
Yes.
Okay, so the gain will be condensed if we also include the peripheral operation of the user equipment. However, given that we lower the transmit power, we expect that we will have a gain, and it will be comparable to this one.
Well, I'm not so sure about the comparable ones, so that's why I'm warning you. I've done a lot of power consumption calculations when I was in Orange, and I was astonished how little the physical layer actually consumes. So the bit per joule or joule per bit is almost not visible in terminals today anymore. Your terminal dies because the Wi-Fi is on or the 3G is on. Now, if you switch that off, that's a good thing. But you know, even 20% or 100% savings or 200% savings on the physical layer, in the end, it translates to very little in terms of your terminal life. I'm just telling you because people get about green and all this, you know. So take everything very relative.
Okay, this is why I stated that it only corresponds to the transmit power.
Yes, no, very good. Okay. Any other questions? If not, then thank you very much. Yes.